Most people think the main problem with space is distance. It's far, it's expensive, and it takes a long time to get anywhere. That sounds reasonable, but it's not the real issue. The real problem is much simpler and much worse. Space is an environment humans were never meant to exist in. Not emotionally, not culturally, physically. Every time we send people into orbit, we're not testing courage or ambition. We're testing how long the human body can function while being slowly pushed outside its biological limits. On Earth, we survive because the planet does most of the work for us. The atmosphere blocks harmful radiation. The magnetic field protects us from charged particles from the sun. Gravity keeps our bones strong, our muscles active, and our organs where they belong. None of that is optional. Take any one of those away, and life gets harder. Take all of them away at once, which is exactly what happens in space. And survival becomes a constant struggle against physics itself. Astronauts don't leave Earth and enter a slightly tougher version of home. They enter a completely different physical system. In low Earth orbit, astronauts are exposed to significantly higher levels of radiation than on the surface. NASA has measured this for decades. It's not science fiction, and it's not speculation. Radiation damages DNA, increases cancer risk, and accumulates over time. You don't feel it happening. There's no warning signal. The damage adds up quietly, mission after mission. Then there's microgravity. People often say astronauts are weightless, but that's misleading. They are constantly falling around Earth, which removes the mechanical stress our bodies depend on. Bones lose density, muscles weaken, eyes change shape, affecting vision. The immune system behaves differently. These effects were not guessed. They were measured on real astronauts aboard real space stations. Even after returning to Earth, some changes take months or years to recover from. Some may never fully reverse. What makes space especially dangerous is that it looks calm. There are no explosions outside your window, no obvious predators, no dramatic warning signs. Most of the threats are invisible and slow. A little more radiation each day, a little less bone mass each month, a little more strain on systems that evolved for a planet, not a vacuum. This is something Plait has emphasized many times. Space doesn't attack you violently. It wears you down quietly. This is why optimism about long-term human space living needs to be grounded in reality. Technology helps, but it doesn't erase biology. Shields reduce radiation, but don't eliminate it. Exercise slows muscle loss, but doesn't stop it. Life support systems work until they don't. Spaceflight isn't about conquering a hostile frontier. It's about managing constant risk in an environment that never stops applying pressure. Understanding this doesn't mean space exploration is pointless. It means we need to be honest about what we're doing. Humans are visitors in space, not natives. Every second we survive, there is borrowed time, bought with engineering, planning, and sacrifice. Space doesn't care that we're curious. It doesn't care that we're smart. It follows the rules of physics. And those rules were written long before humans ever looked up at the stars. One of the biggest misunderstandings about space is radiation. Many people imagine it as something rare, like a sudden solar flare or a dramatic cosmic event. In reality, radiation in space is constant. It's always there. Astronauts don't wait for danger. They live inside Nego every second of the mission. This isn't hidden information. NASA has published radiation data for decades, and the numbers are very clear. Even in low Earth orbit, astronauts receive far more radiation than people on the ground. On Earth, most of this problem is solved for us automatically. The atmosphere absorbs a huge amount of high-energy radiation before it ever reaches the surface. The planet's magnetic field bends charged particles away from us. We grow up protected, so we rarely think about it. But once you leave Earth, those shields vanish almost instantly. A few hundred kilometers up, and you're already far more exposed than any human ever was before the space age. Astronauts aboard the International Space Station are still partially protected by Earth's magnetic field. Yet they receive roughly 10 times more radiation than someone living on the surface. This isn't speculation. It's measured with detectors worn on their bodies. Over long missions, this exposure increases the risk of cancer, damages cells, and affects the nervous system. You don't feel radiation the way you feel heat or pain. That's what makes it dangerous. It doesn't announce itself. Now imagine going farther. The Moon, Mars, deep space. Once you leave Earth's magnetic field, radiation levels rise sharply. During the Apollo missions, astronauts passed through the Van Allen radiation belts, regions of trapped charged particles around Earth. They moved through them quickly, and even then, radiation exposure was a serious concern. These missions were short by design, partly because staying longer would have increased the risk significantly. This is where science often clashes with popular imagination. Movies show astronauts walking on Mars as if it's just a cold desert. But Mars has almost no magnetic field and a very thin atmosphere. That means radiation from space reaches the surface far more easily. Measurements from orbiters and rovers have confirmed this. Any long-term human presence on Mars would involve continuous exposure to radiation levels far above what's considered safe on Earth. Shielding helps, but it's not a perfect solution. Thick walls reduce radiation, but they add mass. Mass makes launches harder, more expensive, and more dangerous. Some types of radiation are so energetic that they pass through many materials anyway, creating secondary radiation inside the shield. This is one of those uncomfortable facts of physics. There's no simple off switch for cosmic radiation. What makes this especially important is time. A short mission can tolerate risks that a long mission cannot. A few days, maybe weeks, manageable. Months or years? That's when the math starts to look bad. Radiation damage accumulates. It doesn't reset when you sleep. It doesn't care how advanced your spacecraft is. This is why discussions about permanent space habitats always run into the same wall. Biology doesn't scale the way engineering dreams do. Plait has pointed out many times that space is not trying to kill us in a dramatic way. It's not hostile like an enemy. It's hostile in the way a vacuum is hostile, or deep ocean pressure is hostile. It simply exists under rules that don't match our biology. Radiation is one of the clearest examples of that mismatch. It's invisible, unavoidable, and always present once you leave Earth. So when people ask why humans haven't gone farther yet, radiation is part of the answer. Not fear, not lack of ambition, just physics. The universe is filled with high-energy particles moving at near light speed. And Earth happens to be a rare place where we're mostly protected from them. Step outside that protection, and the clock starts ticking in ways most people never notice. Until the data makes it impossible to ignore. When people watch astronauts floating inside the space station, it often looks fun. Weightlessness feels like freedom. No up or down. No heavy body to carry around. But what looks like a bonus is actually one of the most serious problems of spaceflight. The human body is built to work against gravity. Take gravity away, and many of our systems stop behaving the way they should. Bones are one of the first things to change. On Earth, bones constantly rebuild themselves in response to stress. Walking, standing, even sitting applies force that keeps them dense and strong. In microgravity, that stress almost disappears. As a result, astronauts lose bone density at a measurable rate, especially in the hips and legs. This isn't a theory. It's been measured repeatedly on long-duration missions aboard the International Space Station. Muscles follow the same pattern. Without gravity, muscles don't need to work as hard to move the body or maintain posture. Over time, they weaken and shrink. Astronauts spend hours every day exercising to slow this process, not to stay fit, but simply to remain functional. Even with that effort, muscle loss still happens. This tells us something important. Exercise helps, but it doesn't fully replace gravity. One of the more surprising effects of microgravity involves vision. Many astronauts experience changes in their eyesight during long missions. The shape of the eyeball can shift as fluids move toward the head in weightlessness. This condition, now well documented, can cause blurred vision and pressure on the optic nerve. In some cases, these changes persist even after returning to Earth. It's another example of how deeply gravity is woven into human biology. The immune system also behaves differently in space. Studies have shown changes in how immune cells function, making astronauts more vulnerable to infections or causing dormant viruses to reactivate. Again, this isn't dramatic or immediate. It's subtle. But subtle changes matter when missions last months or years. Small weaknesses add up in environments where medical help is limited and evacuation is impossible. Fluids in the body shift upward in microgravity, causing the familiar puffy face and thinner legs seen in astronauts. While this looks harmless, it affects blood pressure regulation and can strain the cardiovascular system. The body tries to adapt, but adaptation doesn't mean improvement. It means compromise. The body is constantly guessing how to function in a situation it was never designed for. Plait has often emphasized that these effects don't mean humans can't go to space. They mean space extracts a cost. Every day spent in microgravity requires compensation, monitoring, and recovery. Astronauts don't return home and instantly resume normal life. Many undergo long rehabilitation to regain strength, balance, and endurance. Spaceflight is not a pause button on the body. It's a stress test. This becomes a serious issue when people talk about long-term missions to Mars or permanent habitats in orbit. A trip to Mars alone takes months each way. Add time on the surface, and you're looking at years in reduced gravity. Mars has gravity, but only about a third of Earth's. We don't fully know how the human body responds to that long term. But everything we've seen so far suggests the problems don't disappear. They just slow down. Microgravity reveals a hard truth. Gravity is not just a force we live under. It's a constant input our bodies rely on to stay healthy. Remove it, and the body starts to unravel in ways that no amount of motivation or optimism can fix. This isn't a failure of will or technology. It's a reminder that humans are deeply tied to the planet that shaped them. When people imagine the mental side of spaceflight, they usually think about fear. Fear of launch, fear of spacewalks, fear of emergencies. In reality, fear is not the main problem. Astronauts are trained for dangerous moments. What's harder to train for is monotony, isolation, and the slow psychological pressure of living in a place where nothing ever truly changes. Life aboard a space station is extremely structured. Every hour is planned. Every task is scheduled. There is very little personal space and almost no privacy. Astronauts live and work in the same small volume for months at a time, surrounded by the same people, the same walls, the same sounds. On Earth, even boring routines are broken up by small changes. In space, repetition is relentless. One of the biggest psychological stressors is isolation from Earth. Astronauts can see the planet through a window, but they can't touch it. They can talk to family, but only through delayed communication. They know that if something goes seriously wrong, help is very far away. That knowledge sits quietly in the background of every day. It doesn't cause panic, it causes tension. And tension, over long periods, changes how people think and behave. NASA and other space agencies have studied this extensively, not just in orbit, but in Earth-based simulations. Crews placed in long-term isolation experiments often report changes in mood, motivation, and group dynamics. Small disagreements feel larger. Minor frustrations linger longer. People withdraw or become irritable, even when everyone involved is highly trained and emotionally stable. Space doesn't turn people into villains. It amplifies normal human stress. Sleep is another major issue. On the International Space Station, astronauts see a sunrise and sunset roughly every 90 minutes. While schedules are set to mimic a normal day, the body's natural rhythm doesn't always cooperate. Many astronauts report sleep problems, even with careful planning. Poor sleep affects attention, memory, and emotional control. Over time, that can become dangerous in an environment where mistakes are costly. Plait has often pointed out that humans didn't just evolve physically on Earth. We evolved socially. We rely on large communities, open spaces, and a constant flow of new stimuli. Space strips most of that away. The social group is tiny. The environment is sealed. Nature, in the way we understand it, is completely absent. There's no wind, no rain, no animals, no unpredictability except for system failures. That absence matters more than people expect. This is especially important when thinking about missions beyond Earth orbit. A trip to Mars involves communication delays of up to 20 minutes one way. That means real-time conversations with Earth are impossible. Astronauts would have to make decisions alone, knowing advice from mission control arrives too late to help in emergencies. This isn't hypothetical. It's a direct consequence of distance and the speed of light. What all of this shows is that spaceflight challenges the mind just as much as the body. And like physical problems, psychological ones don't have simple fixes. Training helps, careful crew selection helps, technology helps, but none of it removes the underlying pressure. Humans are adaptable, but adaptation has limits. Space doesn't break people instantly. It wears on them slowly, day after day, in small, quiet ways. That's why long-duration missions are as much psychological experiments as they are engineering ones. The question isn't whether humans can survive space for a while. We already know they can. The real question is how long they can remain healthy, focused, and emotionally stable when removed from the environment that shaped them. It's easy to think that once you solve the big problems of space, rockets, radiation, gravity, the rest is just details. Oxygen, water, temperature. Basic stuff. But in space, those basic things become the most fragile part of the entire mission. On Earth, life support is invisible. In space, it's a machine that can never be allowed to fail. Every breath an astronaut takes exists because a system is actively working. Oxygen must be generated, circulated, and monitored. Carbon dioxide must be removed constantly, or it builds up to dangerous levels. Water must be recycled again and again, because there is no backup supply waiting outside. These systems are impressive, but they are also complex, and complexity always brings risk. The International Space Station is a good example of how delicate this balance is. It's one of the most advanced machines ever built, supported by multiple space agencies and decades of engineering. And even there, problems happen. Air leaks have occurred. Cooling systems have failed. Sensors have malfunctioned. None of this means the ISS is unsafe. It means space gives you no margin for error. On Earth, a broken air conditioner is uncomfortable. In space, temperature control is a survival system. One side of a spacecraft can be exposed to intense sunlight, while the other faces extreme cold. Without constant regulation, temperatures would swing far outside what the human body can tolerate. This isn't a rare danger. It's a permanent condition that must be actively managed every second. Fire is another risk that behaves very differently in space. In microgravity, flames don't rise the way they do on Earth. They spread in unpredictable ways, consuming oxygen more evenly. Space agencies take this seriously because fire in a sealed environment is one of the most dangerous emergencies imaginable. There's no fresh air to dilute smoke and nowhere to escape. That's why materials, procedures, and even clothing are carefully controlled. Plait has often emphasized that spaceflight is not about eliminating risk. It's about controlling it. Every system on a spacecraft exists to replace something Earth gives us for free: gravity, air, pressure, temperature. On Earth, these things fail gracefully. In space, failure is immediate and absolute. There is no slow transition from safe to unsafe. This becomes even more critical when people talk about space habitats or planetary bases. The moment humans live off Earth, their environment becomes artificial in the most literal sense. The walls are not shelter, they are survival. The air is not background. It is a manufactured product. Even a small failure left uncorrected can cascade into something fatal. That's not pessimism. That's engineering reality. What often gets overlooked is how much constant attention this requires. Astronauts aren't just explorers or scientists. They are also full-time maintenance workers for the systems keeping them alive. Cleaning filters, checking sensors, repairing equipment. Life in space is not passive. It demands continuous effort just to remain stable. All of this adds another layer to the challenge of long-term missions. The longer humans stay in space, the more chances there are for something to go wrong. Wear accumulates. Materials degrade. Systems age. On Earth, time usually helps us adapt. In space, time increases exposure to risk. This doesn't mean humans shouldn't push outward. It means spaceflight is closer to deep-sea diving than to settling a new continent. It's about operating in an environment that never becomes safe, only temporarily survivable. The technology works, but only as long as everything keeps working together, without interruption. And that's the key idea many people miss. Space doesn't need a dramatic disaster to be dangerous. It just needs one small system to stop doing its job. One of the most misleading things about spaceflight is how routine it can appear from the outside. A launch goes smoothly. Astronauts float, smile, do experiments. The mission seems calm and controlled. But behind that calm is a long history of close calls. Situations where a small problem nearly turned into something much worse. These aren't secrets. They're documented, studied, and openly discussed by space agencies because they show how unforgiving space really is. Take oxygen systems, for example. On Earth, oxygen is everywhere. In space, it's a carefully managed resource. There have been missions where sensors gave incorrect readings, making crews unsure whether air was safe to breathe. In other cases, carbon dioxide levels rose faster than expected. Even short exposure to high CO2 can cause headaches, confusion, and poor decision-making. In a sealed spacecraft, that's a serious threat, not an inconvenience. Power is another constant concern. Solar panels provide electricity, but they rely on orientation, sunlight, and functioning hardware. If power drops, systems shut down in priority order. Heating, air circulation, and communication all depend on electricity. Spacecraft are designed with backups, but backups don't mean infinite safety. They mean limited time to fix the problem before conditions deteriorate. One famous example of how fragile spaceflight can be involved a simple mistake in a checklist. A valve left in the wrong position caused oxygen to leak into space. The crew wasn't in immediate danger, but the situation forced rapid decisions under pressure. There was no dramatic explosion, no cinematic countdown. Just quiet tension and problem-solving, knowing that the margin for error was thin. What makes these situations especially challenging is that space doesn't allow improvisation the way Earth does. You can't open a window. You can't call emergency services. You can't replace a broken part unless it's already on board. Every solution must work within the closed system you brought with you. This is something Plait has stressed often. Redundancy helps, but redundancy is still finite. Communication delays also play a role, even in near-Earth missions. While astronauts on the space station can talk to mission control in real time, the decision-making burden still falls on the crew. They are the ones inside the system. They are the ones breathing the air. When something goes wrong, they don't have the luxury of waiting to see what happens next. As missions get farther from Earth, this problem grows. On the Moon, delays are small but noticeable. On Mars, they become unavoidable. By the time advice arrives, the situation may already be over, for better or worse. This shifts responsibility heavily toward the crew and the design of the spacecraft itself. Systems must not only work, they must fail in predictable, manageable ways. Another lesson from past missions is that problems rarely come alone. A minor issue increases workload. Increased workload leads to fatigue. Fatigue increases the chance of mistakes. This chain reaction is well understood in aviation and spaceflight. And it's one reason astronauts are trained to slow down during emergencies, not rush. Space punishes panic and rewards patience. But patience requires mental clarity, which stress actively undermines. What all these events have in common is not drama, but fragility. Spacecraft work because thousands of things go right at the same time. When even one of those things goes wrong, the environment offers no forgiveness. There's no buffer, no natural recovery. Everything depends on preparation and response. This history doesn't exist to scare people away from space. It exists to remind us that success in space has always been narrow. Every safe return represents countless moments where nothing failed, and a few where something almost did. Space exploration has never been about eliminating danger. It has always been about managing it, minute by minute, system by system. And that reality doesn't change as technology improves. Better tools reduce risk, but they never erase the underlying truth. In space, survival is always conditional. There's a comforting idea that danger in space comes from accidents. A failed launch, a broken valve, a bad decision. If that were true, then the solution would be simple. Better engineering, better training, fewer mistakes. But the uncomfortable reality is this. Even when everything works exactly as designed, space is still hostile to human life. Not emotionally hostile, physically hostile, by default. On Earth, life exists in balance with its environment. Our bodies constantly exchange heat, gases, and energy with the world around us. That exchange is so stable we barely notice it. In space, that balance is gone. The environment doesn't support life at all. It actively pulls heat away, removes pressure, and exposes living tissue to conditions that cause damage simply by existing. Take vacuum as an example. It's often treated as nothing, but nothing is misleading. Vacuum is an absence of pressure, and pressure matters. Without it, gases dissolved in blood and tissues behave differently. Moisture evaporates faster. Heat escapes in unexpected ways. This is why spacesuits are not just clothing. They are personal spacecraft. They recreate a tiny pocket of Earth around a human body because the surrounding environment cannot be negotiated with. Temperature is another silent problem. Space is not cold in the way people imagine. It doesn't have a temperature you can feel directly. Instead, heat transfer behaves very differently. In sunlight, objects can heat up intensely. In shadow, they can lose heat rapidly. Without an atmosphere, there's no gentle moderation. This forces spacecraft and suits to constantly manage heat, moving it away from where it builds up and conserving it where it's lost. Stop managing it, and conditions become dangerous surprisingly fast. Then there's time. Time in space isn't just a clock on the wall. Orbits, rotations, and distance change how days are experienced. On the International Space Station, astronauts experience 16 sunrises and sunsets every Earth day. That constant cycling would be disorienting without strict schedules and artificial lighting. The body's internal clock didn't evolve for that. It has to be overridden manually every day. Plait has often explained that none of this is mysterious or dramatic. It's basic physics. Space behaves exactly the way it should, given the laws of nature. The problem isn't that space is broken. The problem is that humans are optimized for one very specific set of conditions, and space violates almost all of them at once. This is why the idea of getting used to space is misleading. You can adapt to some things. You can learn procedures. You can build habits. But your cells don't suddenly stop needing protection. Your DNA doesn't become resistant to radiation because you're brave or motivated. Adaptation has limits, and space pushes against those limits constantly. Even something as simple as eating becomes different. Fluids behave oddly in microgravity. Crumbs float, smells linger. The sensory experience of food changes. These aren't just inconveniences. They affect appetite, nutrition, and morale over time. Small stresses compound when there's no escape from the environment causing them. What keeps people watching these missions succeed is that humans are very good at working within narrow margins. We design systems that hold the line just long enough. We plan missions carefully. We accept risk in controlled doses. But that doesn't change the underlying equation. Space is not passively unsafe. It actively moves systems away from conditions compatible with life. This is the core idea behind the title. Space isn't dangerous because it occasionally does something extreme. It's dangerous because it never stops being what it is. Every second outside Earth is a second spent maintaining an artificial bubble against an environment that applies constant pressure, radiation, and stress. And the longer that bubble has to hold, or the harder the problem becomes. That's why the conversation about living in space can't be reduced to optimism or pessimism. It has to be grounded in reality. The universe isn't waiting for us to arrive. It isn't impressed by our technology. It doesn't adjust to our needs. If humans want to exist beyond Earth, they have to fight physics every moment they're there. And physics, unlike stories, never gets tired. There's a reason most conversations about space focus on one problem at a time. Radiation, gravity, distance, life support. Each of them is complicated on своей own, но в реальности они никогда не существуют отдельно. В космосе все эти проблемы работают одновременно. И именно их сочетание делает среду по-настоящему враждебной для человека. On Earth, when something goes wrong, the environment often helps you recover. If you're tired, gravity doesn't get stronger. If you're injured, the air doesn't become toxic. If a system fails, you usually have time. Space offers none of that. When systems fail in space, they fail into an environment that actively makes things worse, not better. This is why redundancy, backups for backups, is such a big deal in spaceflight. But redundancy has limits. Every extra system adds mass. Every kilogram costs fuel. Every layer of protection increases complexity. And complexity itself becomes a risk. More parts mean more points of failure. Engineers are constantly balancing safety against practicality, knowing they can never add enough protection to make space feel forgiving. People often say, "We'll just build better habitats." But habitats don't exist in isolation. They need power, shielding, maintenance, and constant monitoring. A small leak on Earth is an inconvenience. In space, it's an emergency. A minor power loss on Earth is annoying. In space, it can cascade into loss of heating, loss of air circulation, and system shutdowns. The environment outside doesn't pause while you fix things. This becomes even more obvious when thinking about scale. A few astronauts on a short mission can be supported with extreme effort and careful planning. But the idea of large numbers of people living in space changes the equation completely. More people mean more air, more water, more food, more waste, more heat. Every one of those needs to be managed inside a closed system. On Earth, ecosystems absorb mistakes. In space, mistakes accumulate. Plait has pointed out that space exploration often gets framed like exploration on Earth, as if it's a matter of reaching a place and then figuring things out. But space isn't a place you arrive at and adapt to. It's a condition you're exposed to. And exposure doesn't end when you land somewhere. Orbit, Moon, Mars, the physics follows you everywhere. Mars is a good example of this misunderstanding. It's often described as a backup Earth, but it lacks almost everything that makes Earth forgiving. The atmosphere is thin. The magnetic field is weak. Gravity is low. Dust affects machinery. Radiation reaches the surface. Even standing on solid ground doesn't remove the hostility of the environment. It just changes its shape. Another thing that keeps people watching is the idea that future technology will solve these problems. And technology does help, a lot. But technology doesn't change biology overnight. Humans don't suddenly stop needing gravity. Cells don't stop reacting to radiation. Bones don't stop responding to stress. Technology can reduce harm, slow damage, and buy time. It cannot erase fundamental limits. This is why long-term space living is such a different challenge from short missions. Short missions accept damage because recovery happens on Earth. Long-term missions don't have that luxury. Every compromise becomes permanent. Every bit of damage matters more. Space doesn't reset you. It carries your changes forward. What makes this uncomfortable to think about is that there's no single dramatic villain. No one force you can defeat. No final breakthrough that makes space safe. The hostility of space is quiet, constant, and distributed across everything humans rely on to live. And that's exactly why it deserves honest discussion. Because the biggest danger isn't that space is hard. It's that it looks manageable, right up until the costs start adding up. When people imagine future spacecraft, they often picture advanced machines doing most of the work. Smart systems, automation, artificial intelligence, and all of that matters. But no matter how advanced the technology becomes, the human body remains the weakest link in the system. Not because humans are poorly designed, but because space is fundamentally incompatible with how we work. Machines tolerate space far better than people do. Electronics can be shielded. Metals don't lose bone density. Circuits don't need oxygen or sleep. When something breaks, a machine doesn't get tired, scared, or confused. Humans do. That doesn't make astronauts unreliable. It makes them human. And space magnifies every human limitation. Decision-making under stress is a good example. Astronauts are trained extensively, but training happens on Earth, under Earth conditions. In space, stress builds differently. Fatigue from poor sleep, physical changes from microgravity, background anxiety from constant risk. All of that affects how decisions are made. Even small delays or misunderstandings can matter when systems operate close to their limits. There's also the issue of long-term performance. Humans are adaptable, but not indefinitely. Over time, attention drifts. Motivation fluctuates. Mental sharpness varies from day to day. On Earth, those variations are normal and often harmless. In space, where tasks are complex and consequences are high, they become more significant. This is one reason mission schedules are carefully planned to avoid overload. Plait has talked about how spaceflight doesn't reward heroics. It rewards consistency, doing the same careful actions, the same checks, the same procedures, day after day. That sounds simple, but over long periods, it's mentally demanding. Humans crave change and novelty. Space offers routine and constraint instead. Even communication reflects this vulnerability. Astronauts must constantly translate technical issues into clear descriptions for people on Earth. When delays increase, as they would on deep space missions, that feedback loop weakens. The crew becomes more isolated in decision-making, carrying more responsibility with fewer external inputs. That's not a flaw in design. It's a consequence of distance and the speed of light. Another overlooked factor is recovery. On Earth, mistakes are often survivable because the environment supports healing and rest. In space, recovery is harder. The body heals differently in microgravity. Medical resources are limited. There's no hospital down the street. Every problem must be managed in place with what you have, by the people already under pressure. This is why space agencies are so cautious about crew size, mission length, and task complexity. It's not because astronauts aren't capable. It's because humans are not interchangeable components. Each person brings strengths, weaknesses, habits, and limits. Space systems have to be built around those realities, not idealized versions of human performance. The uncomfortable truth is that spaceflight works best when humans are protected from space as much as possible. Thick walls, careful schedules, artificial environments. The more space reaches the human directly, the worse the outcome tends to be. This flips the usual narrative. Exploration isn't about immersing ourselves in space. It's about insulating ourselves from it. And that brings us back to the core idea again. Space doesn't become safer as we get better at visiting it. We get better at temporarily surviving there. The hostility doesn't fade. We just get more skilled at holding it back. As long as humans remain biological organisms shaped by Earth, that tension will never disappear. Space will always demand more attention, more protection, and more compromise than any environment we evolved to handle. And that's not a reason to stop exploring. It's a reason to be honest about what exploration actually costs. There's a quiet shift happening in space exploration, and многие зрители ее почти не замечают. Чем больше мы узнаем о космосе, тем яснее становится одна вещь. Для большинства задач человек там не нужен. И это не потому, что люди бесполезны, а потому что среда настолько враждебна, что машины справляются с ней проще и надежнее. Robotic missions don't need air, water, or pressure. They don't care about radiation the way human cells do. They don't lose bone density. They don't suffer from isolation or fatigue. A probe can sit in deep space for decades and keep working, as long as its systems hold. A human can't. Это не философия, это наблюдение. Mars rovers are a good example. They move slowly, make mistakes, and sometimes fail. But they also survive environments that would kill a human quickly. Thin atmosphere, high radiation, extreme cold, dust everywhere. They don't complain. They don't need rest days. And when something goes wrong, the loss is tragic, but not fatal to anyone involved. Plait has often made the point that robotic missions are not a lesser form of exploration. They are often the smartest option. They gather data continuously, without the massive overhead required to keep people alive. When we send humans, most of the mission is about supporting the humans. When we send robots, almost all of it is about science. This doesn't mean humans have no role. Humans are excellent at improvisation, pattern recognition, and creative problem solving. On short missions, close to Earth, those strengths matter a lot. But the farther you go, and the longer you stay, the more the environment favors systems that don't need protection from it. There's also a cost reality here. Launching humans requires redundancy on top of redundancy. Life support, escape systems, medical planning, psychological support. Every kilogram devoted to keeping a person alive is a kilogram not devoted to instruments or fuel. For robotic missions, that trade-off doesn't exist in the same way. What makes this uncomfortable for many people is that it challenges a familiar narrative. We like the idea that exploration means humans physically being there, standing on the surface, planting flags, leaving footprints. But science doesn't care about symbolism. It cares about data. And data often comes cheaper, safer, and faster from machines. This is especially relevant when people talk about colonizing space. Colonies imply permanence. Permanence means long-term exposure. And long-term exposure amplifies every problem we've already talked about. Radiation, gravity, isolation, system failure. Robots don't face those limits. Humans do. The question then isn't, can robots replace humans in space? They already do in many ways. The real question is why we insist on framing this as a competition. Humans and robots are tools, different tools for different jobs. The mistake is assuming that every destination humans can imagine is a destination humans should physically occupy. Space doesn't reward mere presence. It rewards resilience. And resilience, in many cases, is easier to build into machines than into biology. Understanding this doesn't diminish human achievement. It clarifies it. When humans do go to space, it's not because machines couldn't do the job. It's because we chose to accept the cost, the risk, and the limits. And that choice only makes sense when we're honest about what space actually is. Not a place waiting for us, but an environment that constantly pushes back. The idea of a second Earth is one of the most powerful stories in space exploration. A backup planet, a place we can move to if something goes wrong here. It sounds practical, even responsible. But that idea didn't come from physics or biology. It came from psychology. Humans are very good at imagining familiar solutions to unfamiliar problems. When we picture another world, we tend to picture Earth with small differences. A bit colder, a bit farther from the sun, maybe red dust instead of blue oceans. But deep down, the expectation is comfort, breathable air, open skies, gravity that feels normal. And that expectation quietly ignores how rare those conditions actually are. Earth works because many things line up at once. The right distance from the sun, a thick atmosphere, a strong magnetic field, active geology that recycles carbon, liquid water on the surface for billions of years. None of these alone make a planet habitable. It's their combination, maintained over immense time, that makes Earth forgiving. Remove just one, and the system becomes far less friendly to life, especially complex life. Mars shows this clearly. It likely had liquid water in the past. It has seasons, a day not much longer than Earth's. On paper, it sounds close. But in reality, it lost its magnetic field long ago. Its atmosphere thinned, radiation increased, water retreated underground or escaped into space. The planet didn't fail. It followed physics, and physics doesn't care about habitability. This is why discovering an Earth-like exoplanet doesn't mean discovering an Earth-like home. When astronomers talk about habitable zones, they're describing where liquid water could exist, not where humans could thrive. That distinction often gets lost in headlines. A planet can be in the habitable zone and still be deadly to us in dozens of ways. Plait has often warned against overselling these discoveries. Not because they aren't exciting, they are, but because excitement can turn into misunderstanding. Finding planets tells us how common worlds are. It doesn't tell us how common Earths are, and those are very different questions, very different. What keeps people watching and dreaming is the idea that with enough technology, we can turn any place into home, build domes, generate air, shield radiation. And to some extent, that's true, for short periods. But the longer you stay, the more the environment pushes back. A planet doesn't become Earth just because humans arrive. It continues being itself. This is where the title matters again. Space is not passively waiting to be shaped. It actively resists life as we know it. Planets don't offer neutrality. They offer conditions, and most conditions in the universe are far outside what human biology can tolerate without constant support. The dream of a second Earth persists because it feels like control, like an escape plan. But the reality is more complex. There may be places where humans can visit, study, and even temporarily live. That's an incredible achievement. But replacing Earth is a much higher bar than most conversations admit. And that realization doesn't make space exploration smaller. It makes Earth more remarkable. One of the hardest things to really understand about space is time. Not time as a number on a clock, but time as a physical scale. Human lives are short. Human projects are even shorter. Space, on the other hand, operates on timescales that barely intersect with our own. And that mismatch creates another layer of hostility we rarely talk about. On Earth, change usually happens fast enough for us to respond. Climate shifts over centuries. Ecosystems recover within generations. Technology evolves within decades. Space does none of that. Planets change over millions or billions of years. Orbits drift slowly. Radiation damage accumulates relentlessly, with no recovery phase. If something goes wrong out there, waiting it out is usually not an option. This matters because many ideas about long-term space living quietly assume stability. A base that lasts, a colony that grows, a system that can be maintained indefinitely. But in space, indefinitely is a dangerous word. Materials degrade under radiation. Seals weaken, electronics age. On Earth, maintenance happens within a supportive environment. In space, maintenance happens while the environment continues to attack the system you're trying to preserve. Even planets are not stable in the way we instinctively expect. Mars didn't suddenly become hostile. It slowly lost protection over time. The same physical processes that shape planets today shaped Earth in the past and will shape it in the future. The difference is that Earth has remained in a narrow, lucky window for a very long time. That window is not guaranteed elsewhere. This is another point Plait often emphasizes. Space doesn't rush. It doesn't escalate. It simply keeps going. Radiation keeps flowing. Vacuum keeps pulling. Gravity keeps doing what gravity does. Humans, by contrast, need constant renewal. Rest, repair, recovery. When those cycles are disrupted long enough, performance drops and failure becomes more likely. Think about how much effort it takes to keep even a small crew alive for 6 months in orbit. Now stretch that effort across years, decades, generations. Every system must outlast the people who built it. Every mistake becomes part of the long-term structure. Space doesn't forgive shortcuts taken early, because the consequences often appear much later. This is why space exploration has historically favored missions with clear endpoints. Launch, operate, return. The longer the timeline, the more uncertainty dominates. Human planning is excellent at short horizons. It becomes fragile at long ones. Space lives entirely in the long horizon. The universe is also indifferent to urgency. A problem that needs to be solved soon has no meaning outside Earth. A damaged habitat doesn't get worse faster because humans are inside it. It just continues degrading at the same physical rate. The burden of urgency exists only on the human side of the equation. All of this reinforces the same central idea. Space is hostile, not because it's dramatic, but because it's patient. It applies pressure slowly, consistently, and without concern for outcomes. Humans, by contrast, rely on momentum, motivation, and limited spans of attention and care. When you put those two together, you get a fragile balance. One that can work, but only for a while. And that's the pattern repeating through every chapter of space exploration so far. We succeed by respecting limits. We fail when we assume time is on our side. At this point, a reasonable question starts to form. If space is this hostile, this demanding, this unforgiving, why do we keep going? Why spend so much effort, money, and risk pushing humans into an environment that clearly doesn't want us there? The answer isn't simple, and it's definitely not just because we can. Part of it is curiosity. Humans have always tried to understand what's beyond the horizon. Space is the biggest horizon we've ever faced. Studying it answers questions we can't ask anywhere else. About how planets form, how stars live and die, and how the universe itself behaves. These questions aren't abstract. They tell us where we came from and how rare our situation might be. Another part is perspective. Astronauts often talk about how seeing Earth from space changes how they think. From orbit, borders disappear. The planet looks fragile, thin-skinned, and isolated. That view isn't poetic exaggeration, it's accurate. Space shows us how narrow the conditions for life really are. And that realization often strengthens, rather than weakens, the importance of protecting Earth. There's also a practical side that rarely gets enough attention. Space is a harsh testing ground. Technologies developed to survive there often make life better here. Life support systems, water recycling, materials science, medical monitoring. Many of these advances come from trying to solve problems that space makes impossible to ignore. Space doesn't just challenge us, it forces clarity. Plait has pointed out that exploration doesn't require the destination to be friendly. Antarctica isn't friendly. Deep oceans aren't friendly. We explore them not because they welcome us, but because understanding extreme environments teaches us something about limits, including our own. What space exploration is not, despite how it's sometimes framed, is an escape plan. It's not a backup drive for humanity. It doesn't offer safety or comfort. It offers knowledge. And knowledge, historically, has been one of the few things humans are willing to endure hardship for. This is where the narrative often gets confused. Going to space doesn't mean abandoning Earth. In many ways, it does the opposite. The more we learn about how hostile the universe is, the more obvious it becomes how unusually kind our planet has been. Earth isn't just home by chance. It's home because an extraordinary number of conditions line up just right. There's also something deeply human about choosing difficulty knowingly. Astronauts understand the risks better than almost anyone. Engineers understand the failure modes. Scientists understand the limits. And yet, missions still happen. Not because the danger is ignored, but because it's measured, studied, and accepted in controlled ways. Space exploration, at its best, is not about conquering an environment. It's about learning how to exist at the edge of what's possible, without pretending that edge will ever move very far. The hostility doesn't disappear. The challenge doesn't fade. What changes is our understanding of it. And that understanding feeds back into how we see ourselves. We are not a species built for space. We are a species curious enough to visit it anyway. When people talk about the future of humanity in space, the conversation often jumps straight to extremes. Either we become a multi-planet species, spreading across the stars, or we fail completely and disappear. Real history rarely works that way. Progress usually happens in narrower, more constrained steps, and space is no exception. The future we're actually moving toward looks less like science fiction and more like careful, limited presence. Short missions, targeted research, temporary habitats designed for specific goals. Humans visiting space the way scientists visit Antarctica or the deep ocean, with preparation, protection, and the understanding that no one truly belongs there. This isn't a disappointment. It's a correction. For a long time, space was framed as the next natural home for humanity. But the more data we collect, the clearer it becomes that space is not an extension of Earth. It's a boundary, a place where our assumptions break down and where survival requires constant effort. One of the most important lessons space has taught us is humility, not in a philosophical sense, but a practical one. The universe does not adjust to us. It doesn't scale to human comfort. Every success in space happens because we adapt ourselves, temporarily, inside narrow margins. That's not weakness. That's realism. This also changes how we should think about long-term survival. If humanity's future depends on space as an escape, that future is fragile. If it depends on understanding Earth better, using space as a tool to observe, measure, and protect our planet, that future becomes much stronger. Satellites monitoring climate, weather, oceans, and ecosystems have already proven this point. Plait has often argued that loving space and caring about Earth are not opposing ideas. They reinforce each other. Space shows us how rare, stable, life-friendly environments really are. It strips away the illusion that habitable worlds are easy to come by. And once that illusion is gone, Earth stops feeling replaceable. There's also a cultural shift happening. Early spaceflight was about firsts. First orbit, first landing, first steps. Today, it's increasingly about sustainability, reliability, and understanding limits. That shift doesn't grab headlines as easily, but it reflects maturity. We're moving from exploration driven by momentum to exploration guided by knowledge. The idea that humans will someday live comfortably across the solar system isn't impossible, but it's far less likely than people assume. And it would require changes not just in technology, but in biology, economics, and culture. Those changes don't happen quickly, and they don't happen just because we want them to. What space teaches us, over and over again, is that desire doesn't override physics. Optimism doesn't cancel radiation. Ambition doesn't replace gravity. Planning matters. limits matter. And respecting those limits is often what makes success possible in the first place. In that sense, space isn't telling us no. It's telling us be careful, be precise, and don't confuse possibility with permission. The universe allows us to visit. It does not promise to accommodate. It's surprisingly easy to imagine a future in space when you skip the details. A base on the moon, a city on Mars, people living under domes, going about their lives like it's just another place. These images feel familiar because they borrow heavily from Earth. Streets, homes, communities. What's missing from those pictures is the cost of maintaining every single one of those details against an environment that never relaxes. Every future scenario in space has an invisible price tag attached to it. Air must be manufactured, water must be recycled with extreme efficiency. Food must be grown or delivered under tight constraints. Waste must be managed perfectly. Energy must be constant. On Earth, these systems are spread across ecosystems, infrastructure, and time. In space, they are compressed into small, fragile loops that cannot afford disruption. This is where the idea of scale quietly breaks down. Supporting a handful of astronauts for a few months is already one of the most complex things humans do. Scaling that up to hundreds or thousands of people doesn't just multiply the challenge, it changes it. More people don't just need more resources. They create more heat, more waste, more maintenance, and more opportunities for failure inside a closed system. Another detail often overlooked is choice. On Earth, if a place becomes uncomfortable or dangerous, people can leave. In space, there is nowhere else to go. A habitat isn't just a home, it's the only environment keeping you alive. That changes how stress works. It changes how conflict works. It changes how people think about risk. The environment doesn't allow casual decisions. Plait has pointed out that science fiction often treats space living as a solved problem with enough time and ingenuity. Real science treats it as an ongoing experiment with strict boundaries. The difference matters. One assumes inevitability. The other demands constant proof that the system still works today, not just in theory. This doesn't mean the future in space is bleak. It means it's specific, focused, limited. And that limitation is what keeps it realistic. Humans can do remarkable things when goals are clear and conditions are controlled. Problems arise when imagination outruns physics. What keeps space exploration meaningful isn't the promise of comfort. It's the willingness to operate at the edge of what's survivable, knowing that edge doesn't move easily. Space doesn't reward expansion for its own sake. It rewards understanding. When people imagine humans living in space long-term, they often imagine stability, a place that eventually feels normal, a routine that becomes comfortable. But space never becomes normal. Even after months or years, the environment remains artificial, controlled, and dependent on constant attention. There is no moment when space stops demanding effort and simply lets people exist. What makes this difficult to fully grasp is that human comfort is deeply tied to forgiveness. On Earth, mistakes are absorbed by the environment. A missed repair, a bad day, a delayed response. Most of the time, nothing catastrophic happens. In space, systems are not forgiving. Small issues accumulate, and accumulation is dangerous in closed environments. This is especially clear when thinking about generations. The idea of children growing up in space is often presented as a symbol of success. But biology complicates that picture. Human development relies on gravity, stable radiation levels, and complex sensory input from the natural world. We don't fully understand what long-term space conditions would do to a developing body or brain, and not understanding is not the same as safety. Radiation exposure, for example, is often discussed in terms of adult risk, cancer probability, lifetime dose. But children are more sensitive to radiation damage, especially during development. This isn't speculation, it's well established in medical science. Space doesn't lower that risk. It increases it, and shielding can only reduce, not eliminate, exposure. Gravity is another unknown. Bones, muscles, and organs develop in response to mechanical stress. Reduced gravity changes how that stress is applied. We have data from adults adapting poorly to microgravity. We have very little data on development in partial gravity over long periods. Assuming it will probably be fine is not a scientific position. Plait has often stressed that space exploration works best when it respects what we don't know. Confidence without data is not optimism. It's risk. The farther humans move from Earth, the harder it becomes to test assumptions safely. And once a population exists off-world, reversing course becomes ethically and practically complex. This adds another layer to the hostility of space. It's not just about surviving today. It's about sustaining health across time, across people, across generations. Space doesn't provide a stable backdrop for that. It provides a constantly shifting set of constraints that biology must continuously fight against. What makes this uncomfortable is that it forces a reassessment of what success actually looks like. Success may not be permanent settlements or growing populations. It may be limited presence, careful missions, and deep understanding gained without pretending the environment will ever stop pushing back. A common mistake in thinking about space is assuming that once humans arrive somewhere, the hardest part is over. That the act of getting there is the main challenge. In reality, arrival is often the easiest phase. The real difficulty begins after, when systems must keep working day after day without interruption, repair delays, or environmental support. On Earth, infrastructure exists inside a living system. Air, water, soil, and biology all absorb stress and smooth out failures. In space, infrastructure exists in isolation. There is no surrounding system to help it recover. Every component must function within strict limits, and every limit is enforced by physics, not convenience. This is why space missions are designed with extreme caution and narrow objectives. Not because engineers lack imagination, but because imagination doesn't override constraints. Each added goal increases complexity, and complexity increases risk. In space, risk doesn't spread out. It concentrates. People often underestimate how mentally taxing constant vigilance is. Knowing that your environment depends on machines that must never stop working changes how you think. There is no true downtime. Even rest happens inside a system that requires monitoring. Over time, this awareness becomes a background pressure that never fully disappears. Plait has pointed out that humans are excellent at solving problems, but not at living indefinitely in problem-solving mode. Space living requires sustained attention without relief. On Earth, nature provides cycles of effort and recovery. In space, recovery must be engineered, scheduled, and enforced. This leads to an important realization. The difficulty of space is not that it occasionally becomes dangerous. It is that it never becomes safe. Safety is not a state you reach. It is a condition you actively maintain. The moment attention drops, the environment begins to win. Another assumption that often goes unchallenged is that future technology will naturally make space easier. History suggests the opposite. As systems become more advanced, they often become more interconnected. Interconnection improves performance, but it also increases the chance that small failures propagate through the system. In space, cascading failures are especially dangerous. A power issue affects life support. Life support affects crew health. Crew health affects decision-making. Decision-making affects repairs. None of these exist in isolation. The environment outside does not slow this chain down. It applies constant pressure throughout the process. This is why engineers design space systems to fail in predictable ways. Not to prevent failure entirely, but to control how it unfolds. That approach works, but only within limits. Over long durations, unpredictability increases. Materials age, sensors drift, tiny inefficiencies compound. Time amplifies everything in space. A small design compromise that is acceptable for weeks may become unacceptable over years. A workaround that functions for one mission may quietly create problems in the next. Space does not reset between attempts. Lessons are learned, but conditions remain harsh. This is another reason why permanent human presence in space is such a high bar. Permanence requires stability, and stability requires an environment that supports equilibrium. Space does neither. It constantly pushes systems away from balance, forcing continuous correction. The longer humans remain in space, the more resources must be devoted not to progress, but to preservation. Maintaining the status quo becomes the primary task. Exploration slows. Expansion becomes harder. The environment does not reward endurance. It taxes it. People often ask whether humanity will eventually overcome these limits. The honest answer is that some limits can be managed, but others are fundamental. Radiation can be reduced, not eliminated. Gravity can be simulated, imperfectly. Isolation can be mitigated, but never fully removed. These are not engineering failures. They are properties of the universe. What makes space exploration valuable is not the promise of comfort, but the clarity it brings. Space strips away assumptions that feel obvious on Earth. It shows which parts of human life are flexible and which are not. It reveals how dependent we are on conditions we rarely notice. This is why space should not be framed as a replacement for Earth. It is not an alternative environment. It is a contrast. A way to understand just how specific and fragile our home really is. Every successful mission reinforces that lesson. Plait has emphasized that science works best when it replaces fantasy with understanding. Space exploration does not diminish humanity by revealing limits. It sharpens our sense of reality. It tells us where ambition must slow down and where care matters more than speed. The future of humanity in space will likely be cautious, selective, and limited. That is not a failure of imagination. It is a sign that imagination has finally caught up with physics. Another idea that often keeps people emotionally invested in space is the belief that difficulty automatically leads to mastery. That if humans struggle long enough in a hostile environment, they will eventually adapt to it in a deep, permanent way. This belief feels intuitive, but biology does not work like cultural progress or technology. Human adaptation is limited by the speed of evolution and the boundaries of physiology. Astronauts adapt behaviorally and temporarily, but their bodies do not rewrite themselves to suit space. Bone loss slows, but does not stop. Muscle weakening is managed, but not erased. Radiation damage accumulates regardless of experience or training. This distinction matters because it separates learning from transformation. Humans can learn how to operate in space, but learning does not mean becoming native to it. The environment remains external and hostile, and the body remains dependent on protection. No amount of familiarity changes the underlying relationship. On Earth, long-term exposure to an environment usually leads to biological balance. In space, long-term exposure leads to biological cost. That cost may be delayed or reduced, but it never disappears. Time does not heal the mismatch between human biology and space conditions. It deepens it. This is why space agencies are careful about how long astronauts stay off Earth. Missions are designed around recovery, not permanence. The expectation is always return, rehabilitation, and readaptation to Earth's gravity and atmosphere. Spaceflight is treated as an interruption, not a new baseline. Plait has repeatedly highlighted that science fiction often assumes humans will simply get used to space. Real science shows the opposite. The longer humans remain there, the more effort is required just to maintain basic health. Adaptation does not trend toward ease. It trends toward management. There is also a tendency to assume that future generations will somehow solve these problems because they will grow up knowing more science. Knowledge helps with decisions, but it does not rewrite physical laws. A better understanding of radiation does not make cells immune to it. Better modeling does not stop gravity from being weaker on Mars. This becomes especially important when people imagine large, self-sustaining space populations. Self-sustaining systems require resilience. Resilience requires buffers. Buffers require environments that tolerate inefficiency. Space does not tolerate inefficiency. Everything must work close to optimal conditions all the time. On Earth, ecosystems absorb waste, recycle materials, and adapt dynamically. In space, all of those processes must be engineered artificially. Artificial systems can be precise, but they are brittle. They work well until they don't, and when they fail, the environment offers no backup. This brittleness is not hypothetical. Engineers plan around it constantly. Maintenance schedules are strict. Margins are thin. Every kilogram of extra material must justify its presence. The environment forces trade-offs that Earth-based systems rarely face. As systems grow larger, these trade-offs become harder to manage. More people mean more interactions, more dependencies, and more points where things can go wrong. Complexity grows faster than safety margins. That is a pattern seen in many engineered systems, and space amplifies it. The hostility of space is not just physical. It is systemic. It challenges any attempt to build large, stable human systems by constantly applying pressure at every level, from molecules to machines to minds. Another reason space feels deceptively manageable is because we mostly see it through success stories. Missions that fail quietly are rarely remembered. Missions that succeed dominate public imagination. This creates a skewed sense of reliability that does not reflect how narrow those successes often are. Every successful space mission represents thousands of controlled risks that did not escalate. That does not mean those risks were small. It means they were managed well, often with little room to spare. Spaceflight history is full of missions that worked because conditions stayed just within tolerable limits. This selective memory matters because it shapes expectations. When people imagine the future, they project past success forward without fully accounting for cumulative stress. But cumulative stress is exactly what long-term space presence would amplify. Plait has stressed that science communication should resist turning success into inevitability. Space exploration works because it is cautious, limited, and honest about risk. Removing those constraints does not make space more accessible. It makes it more dangerous. The lesson here is not that humans should stop going to space. It is that success in space depends on respecting its hostility, not denying it. The moment space is treated as neutral or welcoming, planning becomes sloppy, and sloppiness is not tolerated. One of the most important realizations that comes from studying space honestly is that success there has never meant comfort. Every human mission that worked did so because expectations were limited and carefully managed. Crews were small, durations were constrained, objectives were specific. Space rewarded restraint, not ambition without boundaries. This pattern repeats across decades of exploration. The more focused the mission, the better the outcome. The more assumptions built into it, the higher the risk. Space does not scale gracefully with human dreams. It scales harshly with physics, mass, energy, and time, ignoring that reality has never produced good results. The idea that humanity's future depends on spreading outward often assumes that expansion itself is protection. But expansion into a hostile environment does not reduce vulnerability. It redistributes it. Instead of one fragile system on Earth, you get many fragile systems spread across space, each demanding constant attention and resources. Earth, for all its problems, remains an environment that supports recovery. Mistakes can be corrected, systems can be rebuilt, ecosystems adapt. Space offers none of that flexibility. It requires perfection far more often than humans are capable of delivering over long periods. Plait has often framed space exploration as a mirror rather than an escape. By pushing into environments that strip away safety nets, we learn which parts of our existence are negotiable and which are not. Gravity, radiation protection, atmosphere, and time are not optional features. They are foundations. This understanding changes how progress should be measured. Progress is not how far humans can go while pretending conditions are friendly. Progress is how clearly we understand the limits and work within them without self-deception. What makes space exploration meaningful, despite all of this, is not the promise of living there permanently. It is the clarity it brings back home. Space forces us to confront how specific our needs are and how rare the conditions that support us truly seem to be. The universe is vast, but hospitality is not evenly distributed within it. Most of space is lethal to complex life without constant protection. Earth is not just one planet among many. It is a narrow solution to a very difficult problem maintained over immense time by a rare combination of factors. When people say space is hostile to human life, that is not a moral statement or a warning. It is a description. Space follows its rules consistently. Humans survive there only by temporarily overriding those rules inside carefully maintained bubbles. This does not make space exploration pointless. It makes it honest. Exploration is not about finding comfort elsewhere. It is about understanding reality as it is, not as we wish it to be. That understanding has value precisely because it removes illusion. The future of humanity is not written in the stars as a guarantee. It is written in choices, limits, and care. Space reminds us that survival is not automatic, and progress is not free. Everything that works does so because it is respected, maintained, and protected. In the end, space does not judge human ambition. It does not reward it either. It simply responds to physics, and learning to live with that response rather than arguing against it may be the most important lesson space has ever offered us. If there is one mistake humans repeatedly make when thinking about space, it is assuming that difficulty implies destiny. That because something is hard, it must also be necessary. Space exploration does not work that way. It is not a path laid out for us to follow. It is an environment we briefly enter, study, and leave, carrying lessons back with us. Those lessons are not about dominance or expansion. They are about limits. Space shows us how thin the line is between survival and failure, and how much of our everyday life depends on conditions we did not create. Air, pressure, gravity, and protection are not technological achievements. They are environmental gifts we rarely notice until they are gone. This perspective reframes the entire conversation about the future. The goal is not to escape Earth, but to understand it better. The goal is not to replace our planet, but to recognize how exceptional it is. Space does not offer a backup. It offers contrast, and contrast sharpens understanding. Plait has often emphasized that science is not about making us feel powerful. It is about making us accurate. Space exploration succeeds when it increases accuracy about who we are, where we can go, and what it costs to be there. When accuracy replaces fantasy, decisions improve. Humans will continue to explore space, because curiosity is part of who we are. But exploration does not require illusion. It requires respect for reality. Space will always remain indifferent to our hopes and plans, responding only to physics and time. That indifference is not an insult. It is information. And information, honestly faced, is what allows humanity to make better choices about its future. Space does not want us, but it teaches us why home matters.